Just a few quick announcements. Remember, homework 1 is due on Friday. Please have that in here before lecture on Friday morning. And also, just a general announcement: the tutor room. So I'm only there on Mondays and Wednesdays in the morning. So Monday and then today after at 10:20 or whenever that class starts I'll be in there. But that thing is actually open from 9 to 5 Monday to Friday. I think Monday to Thursday it's open 9 to 5. Friday it's 9 to 1 or something like that. And that is staffed by people who should be able to help you tutoring with any questions you have in this class related to homework. I know there was Jamie was not able to get help yesterday. There was an interpretational issue, so that's on our end. But otherwise, you should be able to get help in there, even if I happen to not be in there during those hours. And that is Calkins Hall, room 134, first floor of Calkins Hall there. So I'd encourage you to check that out if you are still having some issues on the homework. And I know the examples in this class, we sort of hurried through the first chapter, and the examples that we did in lecture were pretty simple, and then kind of jumping to your homework was a bigger jump there. So I apologize for that. That thing I sent around on Monday was working through some sort of intermediate ones that were a little more advanced than what we did in lecture here. So hopefully you had a chance to look at those if you were still struggling on that homework 1 material. Yes, so I think that's all the announcements that I have. Questions, comments from you guys? Everything going okay? All right. Well, we sort of rushed through the end of chapter 2 on Monday, I guess, and I wanted to put up this summary slide, and also before we jump into chapter 3, I want to go through a few more examples to help prepare you for the next homework assignment, which isn't due for a few maybe 8 or 10 days yet. That's a little ways away, but kind of take us past the sort of very basic examples we looked at in the notes. So just a summary here of sort of the important probability rules that we saw in chapter 1, and there are others. These are just sort of the highlights. Remember, we had our complement rule. So this is our complement rule. That if we want the probability for any event A, the probability that it does not happen is equal to 1 minus the probability that it does happen. So the probability of A complements 1 minus the probability of A. We have our number 2 is our general addition rule. So for any two events A and B, if we want the probability of their union, we can just take the sum of their probabilities and then subtract off the probability that of their intersection. So remember, if we have disjoint events, if that probability of that intersection is 0, then you can just turn that union into a sum. Thirdly, we have our rule for conditional probability. For any two events A and B, as long as B has positive probability of A given B is equal to the probability of the intersection divided by probability of B. And that's whatever's to the right of that horizontal line. That vertical line that we know means given. And then also don't forget about Bayes' theorem. That's an important thing you'll see, which is maybe more an application of number 4, which is our general multiplication rule. Probability of A intersect B is conditional probability times marginal probability, just rearranging that formula in number 3. And then we saw that A and B, two events A and B, are independent if and only if the probability of their intersection is equal to the probability of A times the probability of B. And so that is that works both ways. So if A and B are independent, then you can calculate the intersection of their probabilities that way. But it also goes the other direction. If the probability of A intersect B equals probability of A times probability of B, then you can say that they are independent. That goes both ways. That's the if and only if there. So again, these are some of the general rules that you'll need to use here in probability, and again, just kind of a snapshot summary of them here. So again, before we jump into chapter 3, I want to practice using these just a little bit more. These are actually taken from at the end of homework 2. At the end of every homework, actually, there's some suggested exercises, and these are 2 of the suggested exercises from homework 2. And they come from your textbook. So quick first example here is from section 2.4, talking about conditional probability number 60. We see that 70% of the light aircraft that disappear while in flight in a certain country are subsequently discovered. Of the aircraft discovered, 60% have an emergency locator, whereas 90% of the aircraft not discovered do not have such a locator. And then we're going to suppose that some light aircraft has disappeared. And then there's a few questions that are asked next, but before that I wanted to set up a little notation. Again, you can write these out however you want. I'm not grading you on notation on your homework, but I think it can be helpful. So let's let E represent the event that the plane has an emergency locator. And let's let the letter D represent the event that a plane is discovered. And I think it's also good practice to use our notation to write down the information that's given to us, since that's kind of what we'll be using in our formulas. So they've given us three numbers. They've given us a 70%, 60%, and 90%. So what is 70%? What's that the probability of, using our notation down here? Probability of D, exactly right. So the probability that a plane is discovered, 70%. The next number they give us is 60%. And what is that the probability of, using our notation? So that's, we're told that of the aircraft discovered, 60% have an emergency locator. Probability of E given D sounds good to me. So that's the probability that the plane has an emergency locator, given that they are discovered. So some slight rewriting of that there. It's maybe a little tricky. And then how about the last one? How about 90%? How about, what is that the probability of? It's another conditional probability. Yes, sir. Probability of not E given not D. What do you guys think? Probability, that sounds good to me. Actually, that's right. Probability of not E. So that's probably that they do not have a locator, given that they are not discovered. Very good. Okay, so that's the first step, is kind of figuring out, well, setting up some notation and figuring out what information we have been given. All right, so first question says, if the plane has an emergency locator, what is the probability that it will not be discovered? So if it has an emergency locator, what is the probability that it will not be discovered? So what probability do we want to know here?
E given not D.
Say it again. Probability of E given not D? Okay, so that's probability of having an emergency locator given that it's not discovered? Right. So we want so it's always important to think about what am I assuming is true? Yeah, so just you had that flipped around. So I'm assuming that the plane has an emergency locator. So it says if the plane has an emergency locator, then something else. So I'm assuming, so I'm going to say given that the plane has an emergency locator, I want the probability that it is not discovered. So probability of D complement given E. And so now we can start to use our rules of probability here. We know that this is the probability of D complement intersect E divided by the probability of E. So that's always true. But now we need to do some other tricks, right? Because we don't have any of that information, right? We don't know what the probability of D complement intersect E and the probability of E is, right? So, anybody have any ideas? Let's start with the numerator. What can we do? How can we rewrite that to find that using something that we do know? Yes. Say that one more time.
Probability of not D times the probability of E.
the probability of not D times the probability of E. So that's right. So that's we can only use. So that was the special case of the multiplication rule if they are independent. We can use. We're not told that they're independent, which is fine. We have a general rule for this. I think it was number. That would be number 4 here, right? So we have the probability of A intersect B, and we can write out what it is there. So applying that to our example here, we can write. There's 2 different ways you can write that, but since we only have certain information, we can write this probability of D complement times the probability of E given D complement. That's just my general multiplication rule. And we have no idea what the probability of E is. Any ideas on how we can find out what that is? So this is going to be a good time to use yeah.
1 minus D of E naught D complement.
Absolutely right. So that we could write this as 1 minus the probability of E complement. That is certainly true. But again, we don't know what probability of E complement is. What we're told here is we're given this information here. So when you have a bunch of conditional probabilities given to you, the best plan is to probably use Bayes' theorem, or the law of total probability, if you remember that from the chapter 2 notes. So in this, we can write the probability of E as the probability of D times the probability of E given D plus the probability of D complement times the probability of E given D complement. And again, you can draw a picture to convince yourself that that is the right way of doing this. So those 2 things in the denominator are disjoint events. So the first one, probability of D times the probability of E given D. This is the probability of E intersect D. This other one is the probability of E intersect D complement. So I'm just adding up that piece with that piece, and I've broken them out into those conditional probabilities because that's the information that I've been given. So that's just the law of total probability there for the denominator. So I'm going to erase that. Everybody okay with where we've gotten to here? Okay, so now we actually have all this information, or we should be able to calculate all this now. So what's the probability of D complement? Well, the probability of D is 0.7. So what about D complement? That's right, 0.3. And again, we don't know what the probability of E given D complement is, but we do know the probability of E complement given D complement. So what should the probability of E given D complement be? Should be 0.1. This thing equals 1 minus the probability of E complement given D complement. Okay, so that gives us half of the bottom, 0.3 times 0.1. For the other half of the denominator, we have probability of D. We know that that's 0.7, and the probability of E given D. Well, good news, we do have that given to us. So that's the second thing there. That's the 60%. And we can calculate this out to get 0.067. Everybody with me? All right. One more question on this problem. Similar question here. If the plane does not have an emergency locator, what is the probability that it will be discovered? So very similar idea here, kind of exact same thing we just did. What's the probability that I want here? So it's a conditional probability. Probability of D given E complement. Sounds good. So we're saying it does not have an emergency locator, and what is the probability that it will be discovered? So the probability of D, the probability that it is discovered, given that it does not have an emergency locator. I'll go through this a little more quickly. This is the probability of D intersect E complement. This is our general rule of conditional probability. On the top, we can use the multiplication rule. So this is the probability of D times the probability of E complement given D. And on the bottom, we could write out the same thing that we did before. So this probability of D times the probability of E complement given D. Probability of D complement times the probability of E complement given D complement. Say how we got the denominator again? Yeah, so it's going back to that picture. So here's E, here's D. If I want the probability of E, I can add up these two shapes. So this one here is the probability of, or this set anyway. This is E intersect everything that's not in D. And this piece here is E intersect D. So I'm using the law of total probability here, which is page 11 of your chapter 2 notes. And then, so if I want the probability of this thing, I can write that out. Probability of D complement times the probability of E given D complement. That's just my general multiplication rule. And I can do that with both pieces and add them up. Yes?
So should that equation have, I mean, you have E complements on the bottom throughout. Is that supposed to be like that?
Yes.
That doesn't match what you have up there. You have just regular.
True. Yes, so that's a good point. So if I want probability of E complement intersect with D, that would be, well, so if I want the probability of E complement, that's going to be this entire green thing. So yes, so I could make that probability of E complement. I could do the same thing. I just wrote that the other way. Or you could make that, you could let that circle represent E complement would be the same thing. So that's just the general way of how I did that there. Okay, what's another way that I could get the probability of E complement based on part A?
Did you just say 1 minus the denominator?
Exactly right. So we over here we found that the probability of E was equal to 0.45. So the probability of E complement. You could calculate it either way; you'll get the exact same thing. So this is also equal to probability of D, probability of E complement given D, and by 1 minus the probability of E. And that's only a shortcut because we already did part A. So now we can fill in the numerator. Probability of D is 0.6. The probability of E complement. Probability of E complement given D. What is the probability of E complement given D? 0.4, right? So that's going to be 1 minus the probability of E given D. So again, I'm just taking the complement of that event with the conditional bar there. Doesn't matter. Those two probabilities still need to add up to 1. So times 0.4. So yes, the probability of D is 0.7. But I'm looking at the conditional probability there.
He's talking about the other one. Your probability is 0.6. On the next page. Yeah, 0.6 times 0.4.
Oh. Keeping me honest. Thank you, guys. That's correct. And then, again, you could calculate the numerator as it's written either place there. I'm going to take the shortcut and write 1 minus 0.45. And that's 0.5091. Mm-hmm.
So that was just the general multiplication rule.
Yeah, so we've crammed in a whole bunch of rules kind of in very quick steps here. So let's so right here we use the the conditional probability rule. To go from here to here, we use the general multiplication rule. Down here we used the law of total probability. And then again, it's just kind of thinking about what information have I been given and what information am I trying to figure out here. Is everybody okay with this here? All right. So this is again a little more advanced than what we did in the notes. Give you a little sense of how we can piece all these rules together to find the right answer. All right, one more question here. This is maybe a little faster. This is from section 2.5, number 71. It's talking about 2.5 is our section on independence. So the question says, an oil exploration company currently has 2 active projects, one in Asia, the other in Europe. Let A be the event that the Asian project is successful, and B be the event that the European project is successful. So now we're told to assume that they're independent with probability of A equals 0.4 and probability of B equals 0.7. And this will often be the case when we're dealing with independence. Is that we'll just say assume these things are independent. So when you're dealing with independence, it'll often be something that's sort of like this. Okay. First question, if the Asian project is not successful, what is the probability that the European project is also not successful? So let's practice again using our notation to write this down. So what is the probability that I'm looking for here? And I'll give you a hint that it's a conditional probability. Yeah. Right, so I'm assuming the other way around, right? So the Asian project is A, right? Yeah. So I'm assuming that the Asian project is not successful. So given that the Asian project is not successful, the complement of A, I want to know the probability that the European project is also not successful. So probability of B complement given probability of A complement. Yes?
Would we look at this different if they were disjoint instead of independent?
Would we look at this differently if they were disjoint and not independent? Yes. Yes. So if they were disjoint, that's again, we saw last time, that's sort of completely the opposite of being independent. So hold that thought. And I'll show you kind of where we can use independence in here. So I guess to start off with, ignore whatever information you've been given. We can always write out what this thing is, right? We can just use our rule of conditional probability. This is the probability of A complement intersect probability of B complement. And then what do I want to divide by here? Probability of A complement. Exactly right. Okay, so now we could get to your question. So now we're at a place where if we're told that events are independent, then we can go one way. If we're told they're disjoint, we can go a different way. Since we're told that they're independent, we know what we can do with the probability of an intersection. And if it was something else, if it was disjoint, then we could go a different direction. But since we have independence, we can use those rules. So what we know is that the probability of A intersect B equals the probability of A times the probability of B if A and B are independent. So it's not quite what we have, right? We have the probability of A complement intersect B complement. But the very last fact on page 13 of your chapter 2 notes gave us some good information here, that if A and B are independent, then any combination of their complements are also going to be independent. So if A and B are independent, then so is A complement B complement, intersect B complement. So we also know A complement and B complement are independent. So because A and B are independent, A complement and B complement are also independent. And that would work for A complement is independent of B, A is independent of B complement, all those things hold. So since A complement and B complement are independent, how can I change this numerator? Exactly right. So I can change that intersection, take it outside the probability, and make it a multiplication. And now a few things cancel. We just have the probability of B complement, which is 0.3. So what's there is a faster way of doing this? Does anybody pick out what that would have been? A little slower. What'd you say?
You can just ignore A altogether.
Exactly right. So again, the other thing that we know about independent events, that is, so if A and B are independent, then the probability of A given B equals the probability of A. So now we're shuffling the letters around, I guess, there a little bit. But since A complement and B complement are also independent, that conditional probability, we could just jump straight to that step there and be done. So as usual, there's many ways to solve these. Not many, but there's usually more than one way to solve these questions about probability. Yeah, question.
So you'd still want to show the B given A, B not given A not in the work. Like you would just think that logically.
Yeah. So good question. What would I like you to show in your homework if this was a homework problem? I guess I would like you to write out probability of B complement given A complement, but you're fine to jump right to the last step if you say because B complement and A complement are independent. That would be totally fine. Yep. Okay. Part B here, what is the probability that at least one of the two projects will be successful? Okay, so I think, well, here I'll show you how I did this first, and then there's also a little faster way to do it as well. So if I want the probability that at least one of the two projects will be successful, how do I get there? At least one successful. Well, I can put together a bunch of disjoint events. So I can say, well, this is the probability that A is successful and B is not successful. Right? That's having only one of them be successful. I can union that with the probability that A is not successful and B is successful. Or I could have them both be successful. That's okay, right? If they're both successful, that would be true that at least one is successful. So then I could also add in the probability that they are both successful. Yeah?
Why would you use intersections as opposed to like givens?
So why would I use intersections instead of givens?
Like the probability of A given not B as opposed to probability of A intersecting that B.
Yeah. So why would I write this instead of A given not B, something like that? Good question. So that's a different probability. So A intersect B complement means that then I'll find the probability that A is successful and B is not successful. The top one there is slightly different. You would read that as the probability that A is successful given that B is not successful. It's kind of like a given B complement, you're assuming that B is not successful, and then you want to know what's the probability that A is successful. Whereas what we actually want to know is we don't want to assume that B is not successful. We just want to know the probability that A is successful and B is not successful. Have I convinced you? No?
If they're independent, isn't that just the probability of A?
That in this case, that would be just the probability of A, if that's what we were looking for. So I guess we're breaking it down here. I want to know the probability that at least one is successful. So it's kind of like how can it be that at least one of them is successful?
I just did almost the exact same thing. It's probability of A given not B, probability of B given not A, plus probability of A given B.
Yeah. So that's just a slightly different probability that you're asking for. You're assuming, you're saying you're conditioning on the fact that B was not successful, and then finding probably that A was successful. And that's not the same as the probability that A is successful and B is not successful. So it's slight difference there. Is this making sense to everyone else? Is that okay? Well, so I'll show you maybe the easier way to do this, and that might clear this up too, or convince you that this is okay. Anyway, so I have the probability of 3 events union together. They're all disjoint events. Convince yourself of that. So this is going to be the probability of A intersect B complement plus the probability of A complement intersect B plus the probability of A intersect B. And now, thanks to the fact that they're all independent, we can use our multiplication rule for independent events. Question? No? Okay. So this is the probability of A times the probability of B complement plus A complement times B plus the probability of A times the probability of B. So when I'm intersecting independent events, I can just multiply them together. And we know what all these things are. This is 0.4 times 0.3 plus 0.6 times 0.7 plus 0.4 times 0.7. And that is 0.82. Does anybody see a faster way of doing this problem? Yeah.
You group the probability of A times probability of not B and probability of B.
So you could group the, as in to rewrite this line here, for example, or yeah. Yeah, so there's some ways you could use some algebra to rewrite this line. That's definitely true. But sort of thinking about this in your set notation, your events, is there a faster way to do this? Yeah.
The only other way that could happen is if they both don't happen, so you just do 1 minus that probability.
Exactly. So the only possible outcomes is if they're both not successful. So I could take 1 minus that probability. Were you going to say the same thing? So this is a case where it's helpful to draw a picture, and I did this after I did all that work. So if here's event A and here's event B, what shaded area in there represents the probability that at least one of them is successful? Everything inside the circles, right? So this whole thing right here, and the comment that was just given is we could find the green area, probability of everything else, and subtract that from 1. But we know what the blue shaded area is there, right? What's that the probability of? Yeah, that's just the probability of A union B, which we can write down our general rule. And this will become minus the probability of A times the probability of B, and that will give you the same answer. So that's probably a faster way of doing that. But again, you get the same answer, so either way of doing that is okay. Questions, comments on this part? Okay, one more example here. Part C here. Given that at least one of the projects is unsuccessful, what is the probability that only the Asian project is successful? So let's think about how to write this out, and then see if we can use our rules here. So we want the probability of what? So it's going to be a conditional probability. What am I conditioning on? What am I assuming is true? Yeah. Right. So I'm assuming that that at least one of the projects is successful. That's what we just found, right? So that's I want to assume that at least one of the projects is successful. So I'm assuming that A union B is true. Then what's the probability that I want to find? So given that, what's the other probability that I want? Yeah. A and not B, right? So I want the probability that the Asian project is successful and the European project is not successful. So the probability of A intersect B, given that A union B. So given that at least one of them is successful. Yeah.
In the given part, would you have to subtract A intersection B? Probably both.
So in the given part, wouldn't I need to get rid of the case that they're both? Yeah. So I'm assuming that at least one. So if they're both successful, that's fine. That's fine too. So I just want at least one project being successful. All right. So a little less clear on how to attack this, but let's go ahead and write out our general rule here. Probability of something given something else is just the probability of their intersections. So A intersect B complement intersected with A union B divided by the probability of A union B. The good news is we already found the denominator, so we're all set there. But the question kind of is, what's the intersection of those top two sets? And there certainly different ways of figuring out what that is. I'm going to draw a picture again. So if this is A and this is B, so A intersect not B would be this green area. And then A union B again is this entire shaded in area. So what's the intersection going to be?
Just A given not B.
A given not B. So kind of, I think I heard it over here. Again, the part that they overlap is just the green part, right? So maybe I haven't shaded that in very well. But A union B is that purple area. A intersect not B is the green area. And so we just have the green area if we take that intersection. So that's just the probability. That's just the set itself is just A intersect not B. So this becomes just the probability of A intersect B complement. Denominator stays the same. So we already know what the denominator is. That was the 0.82. Again, the top, what's our fastest way of figuring out what that is? Right, so they're independent events, so we can just multiply them together. Probabilities together, probability of A times the probability of B complement. And so that's going to be 0.4 times 0.3 0.146. All right, so that took a little longer of class than I thought it might, but that's good. It gives us some good practice with sort of set operations and how to use the rules and how to rewrite things. I think the trick is just to play around with these things until you can write them in a way that's something that you recognize or have a rule to solve. Pictures are helpful. Those would be some of the tips that I would give you there, I guess. Any questions on these examples? Are we all okay here? Okay, I'll take your silence as a yes, I guess. Okay, so let's go ahead and get started. Last 10 minutes of class here. Let's start on chapter 3. Here in chapter 3, we're going to talk about something called discrete random variables. So what is a random variable? So in chapter 2, we set up our sort of general terminology of what an experiment is, and looking at certain outcomes of various experiments, kind of very generic language. I'm going to take that a step farther here. So in doing an experiment, you're usually interested in some outcome of that experiment, and this could be any number of things. For example, it could be how long a certain electric part lasts, the lifetime of that thing. The number of components in a unit that fail to last at least 1,000 hours. Kind of a different example, how far people have to drive to get to work in a certain metropolitan area, how much a crop yields, and so on. And so each outcome of an experiment can be associated with a number by specifying a role of association. That sounds really abstract. that's kind of what our formal definition is, which we can say here, that for whatever happens in the experiment, we can find a way to assign a number to that outcome. And that's sort of our formal definition of what a random variable is that it's a function from the sample space into the real numbers. So we're taking certain things from our sample space, whatever's in there, and figuring out a way to assign them to a number. So this is kind of a little picture here that shows how we can take various outcomes or various elements from our sample space and then somehow assign them to a number. So for example, this point here, we're gonna assign this thing to the number 0, and we could do that with other things in there too. So our notation is going to be a random variable is we're going to denote by an uppercase letter, and then whatever the particular value of that random variable is, we'll use a lowercase letter. So for example, capital X of little s, this would be just some outcome in the sample space, capital S. So for example, if this point here is let's say S1, then our current assignment here would say that X of S1 equals 0. We're assigning that outcome in our sample space to correspond to the number 0 there. So that may seem a little abstract at the moment. So let's take a look at an example here. So going back to sort of our classic, very simple experiment, we're going to flip a fair coin twice. So then our sample space, again, we've seen this already. You can get head, tail, head, or tail, tail. And so there's no unique random variable x here. And so for a particular example, we should choose a random variable based on like a question we might want to answer. But let's just give a few examples here. We could let x equal the number of heads. In 2 flips. So that's just again we're choosing that definition ourselves. So we're saying we're going to let our random variable equal the number of heads that we get in 2 flips. And so we can then write down what each outcome in our sample space, the number that corresponds to each outcome. So for example, x of HH, well, obviously we got two heads. X of HT, well, that's the same as if we got a tail and then a head. That would be 1. And then if the outcome we get is 2 tails, well, of course we had 0 heads there. So I have a very simple sample space here. I only have 4 events, and there I can assign my random variable for each one of them. So that's just one example of a random variable. Another one I could set up here. I could also say that x. I can set x equal to 1 if we have at least one head. So I'm going to set x equal to 1 if I have at least one head and 0 otherwise. Another example of a random variable. So similarly, I could write down x of HH. Well, I do have at least one head there, right? So that's a 1. X of HT equals 1. If I get a tail and then a head, well, I have at least one head there still, so that's good. And if I get 2 tails, then I did not have one head show up, so I have a 0 there. It's a very, very, very sort of trivial examples at this point, but just to highlight that for the same sample space, I can have more. There's not just one random variable. I could have kind of whatever I want going on here.
For A.
Yeah.
You got x of HS is 2. How did you get 1 for HT at the 10?
In part A?
Yeah.
So in part A, I'm saying that the random variable is just the number of heads that I get out of 2 flips. So if I got a head and then a tail, that means I had 1 head.
Okay.
And if I flip a coin and get a tail and then a head, well, I still have just 1 head. Okay, moving on, another example here. Going back to our concrete beam example, we can, some of us of course know that this can fail by either shear or by flexure. And suppose we take 3 failed beams and then determine the type of failure for each one of those beams. So our random variable here, we're going to let x equal the number of beams among those 3 selected that failed by shear. So let's list each outcome of the sample space and then write down also the associated value of that random variable. So our sample space up here, we've looked at this one before. Well, we could have them all fail by shear. You know what, I'm only going to write this out once. We've already looked at this example. So the random variable x, if we got all 3 of those beams failed by flexure, then what's my value of my random variable there? I think I heard it 0. So none of them failed by shear. If I have another outcome I could get is that they all fail by shear, in which case, what's my random variable there? 3. And then I have a bunch of outcomes that would give me the same value of my random variable. So if I have FFS, that's the same as x of FSF, same as x of S. Any one of those outcomes gives me a 1. One of them failing by shear. And then there's three other possible outcomes in my sample space. Each of which have 2 of those beams failing by shear. Again, very simple example, just kind of taking each event from our sample space and figuring out how we would map that to a number according to the random variable that we've assigned here. Okay, one more example. We'll finish up with this one. Suppose that we have an experiment to conduct to observe the lifetime of a certain brand of light bulbs. I'm going to let x equal the number of hours that the light bulb lasts. So what is my sample space for this experiment? What are the possible outcomes that I could get here? Yeah. Yeah, right. I could get any non-negative number, right? Any positive number rather. So, assuming the lifetime is not 0, I can set up this interval from 0 to infinity. So, of course, the bulb's not actually going to last an infinite amount of time, but since we don't have an upper bound specified there, we can take all the positive real numbers. So, so that's the possible outcomes that I could get, and then if I'm letting x equal the number of hours that light bulb lasts, my random variable for a certain light bulb is simply just the length of time simply the length of time the bulb lasts. So that one's a little less, that makes a little more sense, so that I'm testing a light bulb, I see how long that particular light bulb lasts, and the number that I assign to that outcome is just how long the light bulb lasts. And if we want to be very picky, we can say that's in hours. Okay, so we'll resume our discussion here with this on Friday. Thank you guys so much for being here. We'll see you on Friday. Have a good day.